Hey there, science fans. Today we're diving into the world of ionic equilibrium. It's all about how ions behave in solutions. Let's break it down. Ionic equilibrium happens when the amounts of ions in a solution stay the same over time. Imagine a crowded room where people are constantly coming and going, but the total number stays relatively steady. That's like ionic equilibrium. Now you might be wondering, how do these ions even get into the solution in the first place? Well, it all starts with dissociation. When you put an ionic compound like table salt, NaCl, in water, it breaks apart into its ions. The positive sodium ions, Na+, and the negative chloride ions, Cl, are free to roam around in the water. This process of dissociation is crucial for many chemical reactions to occur. It's like setting the stage for an ionic party. But wait, there's more to this ionic story. Not all ionic compounds completely break apart in water. Some are a bit shy and like to play a game of back and forth. They can dissociate into ions, but they can also recombine to form the original compound. We call these reversible reactions. Take, for instance, vinegar, which contains acetic acid, CH3COO. When you mix it with water, some of it breaks down into hydrogen ions, H+, and acetate ions, CH3COO. But here's the twist. Some of those ions can also get back together to form acetic acid again. Now, to keep track of this ionic dance-off, we use something called equilibrium constants. These constants, like Kw, K, and Kb, tell us how much of a compound will dissociate at a given temperature. Kw is all about water. It tells us how much water itself breaks down into H+ and O ions. K is for acids, like our vinegar friend, and Kb is for bases. The higher the K or Kb value, the stronger the acid or base, meaning it likes to dissociate more. Now imagine our ionic solution is a bit like a seesaw trying to stay balanced. If we add something to one side, it tilts, but then something interesting happens. The seesaw tries to level itself out again. That's essentially what Le Chatelier's principle is all about. This principle says that if we disturb a system at equilibrium, like our ionic solution, it will try to counteract that change and regain its balance. For example, if we add more acid to a solution, the equilibrium will shift to reduce the acidity. It's like the solution is saying, hey, too much acid here, let's try to balance things out. Another cool phenomenon is the common ion effect. Imagine we have a solution with a weak acid, like our vinegar, and we add a salt that contains acetate ions, CH3COO. Now the solution has an excess of acetate ions. According to Le Chatelier's principle, the equilibrium will shift to counteract this change. It will try to reduce the acetate ion concentration by pushing the reaction backward, causing less acetic acid to dissociate. It's like adding salt to our vinegar solution makes it less acidic. So why should we care about all this ionic equilibrium business? Well, it plays a vital role in many areas of chemistry and even in our own bodies. One important application is in buffer solutions. These solutions are like chemical superheroes that resist changes in pH. They're essential in our blood to maintain a stable pH level, ensuring our bodies function correctly. Buffers rely on the principles of ionic equilibrium to do their job. Another application is in titration, a technique used to figure out the concentration of unknown solutions. It's like a chemical detective game where we carefully add a known solution to an unknown one until we reach a point of neutralization. This point, called the equivalence point, helps us determine the unknown concentration. Understanding ionic equilibrium is also crucial in environmental science. It helps us comprehend things like ocean acidification, where the pH of seawater decreases due to the absorption of carbon dioxide from the atmosphere. In a nutshell, ionic equilibrium is a fundamental concept that governs the behavior of ions in solutions. It's a dynamic process of dissociation and recombination, constantly striving for balance. By understanding these principles, we can unlock the secrets of chemical reactions, biological processes, and even the world around us. Keep those ions in equilibrium and keep those science brains buzzing.